first your imagination and then your color pencils. I think that everybody has color pencils. Graph paper is, you know, for a little while it's probably not as important as this thing, but just any paper will do. Okay, first use your imagination. So imagine you are on vacation. No school, no classes, no summer school, not even this thing. You are on an island, you know, vacation island. There is nothing you have to do, and you have lots of paint. You have lots of paint of different colors. Just, you know, infinite supply of paint, and you have infinite supply of blank paper, blank, not graph paper, but blank paper, absolutely infinite supply. And you can, you know, you have nothing else to do. You can draw all day long. You can paint all day long. You can paint whatever design you do. Then it is possible to paint anything, right? Anything you want. Oh, for example, how about this kind of weird design? Can you do that? So, you want to use exactly 3 different colors. You have red, you have green, and let's say you have brown, like that. So, red, green, brown. And you have a plane. Now, not just piece of a plane, but you have infinite plane. And you want to paint every point of that plane using these 3 colors. You have to use all 3 colors. That's what you want. But you want to do it in such a way that every line on that plane has exactly 2 colors on it. Is that clear? Mm-hmm. So every point is painted either red or green or brown, and all 3 colors must be present. And you want to do it in such a way that every line of that plane has only points of 2 colors. If you have any line, it must have exactly 2 colors on it. It cannot be of 1 color, it cannot be of 3 colors. Every line must be of exactly 2 colors, but all 3 colors must be used on the entire plane. Can you do it? Yeah, try to invent how you can do that. Or, if you think that it is not possible to do that, try to convince everybody that it is not possible and we should not spend time on that.
So, we have to use something.
Can you list the conditions on the board?
No, I already said.
No, I didn't hear one.
Okay. You have to use paint every point on the plane of the plane. You have to use all 3 colors. But every line on the plane must contain points of exactly 2 colors.
And we get to draw the lines?
No, you don't draw the lines because they are there.
So every abstract line, after you've painted the plane, it turns out that no matter what line, if you imagine any infinite line on the plane, on that line there is only exactly 2 colors you'll find.
And that's the last one.
So I can't just
No. It's a blank. It's a plane.
No.
There is no grid. No grid. Just a plane. Just a plane.
And you have to use all 3 colors.
You have to use all 3 colors.
But you don't have to use them equally.
Oh.
Right, or
Do
it's up to
whatever.
you.
Do whatever. Yeah. No, if you are for it, if you would it, sure.
And so
you
your
have to
question
do it.
is it possible or
Try to
make,
invent.
yeah.
Try to invent such a. You know, you are on that vacation island. You have nothing better to do. Just invent. Try to invent a design that satisfies these conditions. possible, you should convince everybody that it's possible.
Well, if you have 3 colors,
Yeah.
then after the 3 colors, then you're gonna have to have at least 3 regions that have different colors.
True.
And you can always find a line that will pass through.
Why?
No, that's not.
So you know how to do that?
No, I'm just not convinced that it's impossible yet.
Oh, okay.
Like you can do stripes like this,
Right, and then I can have a line that goes this way.
but then not every line is going to go through all 3 of those regions. But
Are you
you're
using
making
3 colors then?
I mean, even if you just use like this.
She's not saying every line, she's saying there has to be at least one line.
No, I said every
No,
line.
every line.
I said every line of the plane has to have exactly 2 colors.
You could draw a line that only hits those
Oh.
2.
But you can draw a
But you can
line
draw another.
that's all 3. So she's saying every single line.
So in other words, any
So-
line
So this is not the solution.
contains 3
It's just
colors.
No, every
Oh,
line
no.
has 2 colors.
Right, and I'm saying if any line contains 3 colors, you're done. You haven't done it right. You can't do it.
Or every line can have one.
Well, that's not gonna happen.
You should have.
If you don't have something.
So we're solving problem number 1.
When you draw one across, that translucent, and it will cut the rest of the other colors. And then when I draw translucent, because it's any line, any line.
Yeah, you want to create.
So that every line contains one exactly 2 colors.
You have to have a 3-color drawing where once you make the
Anybody
3-color
solve
painting,
any solutions
any line that I draw on it will only hit 2 colors. Will hit exactly 2 colors.
Exactly, rather than just one color.
I mean, it's fine.
Can they hit the
But
2
that's,
colors
yeah.
more than once?
What?
Can they hit the 2 colors more than once?
What do you mean? The point, every
Like,
point
could it
has
go
to be,
from-
every point has to be painted only one color. Every point
Right,
has
but
only.
every line. So could a line, could it have 2 colors or could they like?
Yes.
If
If you're looking at a line, can it go red, blue, red, blue, red, blue, red, blue, red, blue?
Of course,
That's
okay.
what she's asking.
Yeah, yeah, yeah.
It's just that on any line,
Yeah.
if you look at the colors that are on that line is colored using not 1, not 3, but 2 colors. So it could be all green except for exactly 1 point that's red. Or all red except for, or all red and all, alternating reds and greens, it could be lots of possibilities.
But then if it was like that, you could draw lines that were outside of that point.
I think so.
Okay, good. Then if your answer is yes, I have a different question for you. How many different ways to do that? Essentially different. And then, after you answer that question, I will have some other questions. Okay, Miss Mark knows how to paint,
Danny, you got it?
satisfying these conditions. Anyone else? Okay, could you show us? Or just tell me what to do?
There's color chocolate.
So what do you suggest? I don't see from there. So can you just tell us?
So I drew a line that was half like red and half green.
Okay, let me do that. So I have a line and half of it is green and half of it is red.
And everything else is brown.
And everything else is brown. Okay, do you believe that this is a solution?
Yes.
Well, you said points. Points.
You believe that this is a solution?
What about the horizontal line?
Yes. What about any line that is parallel to that?
Oh, right, of course.
For the line.
If a line is
itself.
parallel to that, it has only one color, and this is not allowed.
And is the place where those two connect, is
Yes.
that,
I'm sorry.
are they intersecting?
What?
No, this is just one single line. This is one single
It has like a
line.
red ray.
So, for example, this is the origin, and
So what color is the origin?
let's say green, and everything to the right of the origin is red.
What if you just had another one that was perpendicular to that,
Mm-hmm.
at the same intersection point, a green ray coming down
Okay,
and a red ray going up?
okay, and then we have something
But then,
like,
there you go, you can see
like that.
easy example of 3 colors.
Now you can hit 3 colors, yeah.
How do you,
So what,
Slice diagonally.
So,
Red
is
line,
that,
brown
does
line.
that work?
No.
I'll
Sorry.
decide for
Why
you
not?
first, and then-
it's the same.
I don't
it's
see
the
why
same
this
as-
doesn't work. Can you explain?
Draw a line that goes through, that intersects the red and the green.
Like the watermelon. So
Red
just
is
to the
green.
right of the origin.
Yes, we can draw something, a line that goes like this, right? And then it will have 3 colors.
does this have to be in a plane?
Yes, it has to be clean. It has to be clean. So that doesn't work either. Because some lines have 3 colors.
Okay, let me have more to say.
What if,
My brain just melted off the button.
Suppose you're doing this with some, let's say, 10th graders, and it's hot, and one of them says kind of in a petulant voice, "Why is this math?" What would you say to this impudent student?
It isn't. So what? You just play with it's a game, why not?
and this is not probably for 40%.
So,
Don't figure this out.
yeah.
What if you took it into quadrants and you did opposite quadrants the same color,
Okay.
but the third color right in the middle?
What do you mean by that?
So
Oh, okay, so
green,
you,
green, brown, brown with a
okay,
red dot
so
right in the
we
middle.
have to, we have
But the
this
whole
quadrant.
quadrants
Yeah,
yeah.
this is all red, right? Okay, and then
opposite is the same color.
same color, okay. All red, now what?
Then you leave the brown on the sides
Yes.
and put a green dot right in the center.
So,
Yeah.
so we have just one single point, which is green, right? We have one single point, which is green. We have, this is actually one straight line. And this is another straight line. Does this work? So on the entire plane, there's only one green point.
Oh,
Does that work?
yeah?
Everybody sees that it works?
Yeah.
I think it works. Now, what about simply
So now you can
Simply
just do
two-
one
two
line.
lines? How about just 2 lines that are red, the intersection is green and everything is brown? Will that work?
Yeah.
Also works.
What about one line?
Say that again?
So,
No,
Just
okay,
two-
one line and get
2 red lines, their point of intersection is green, everything else is brown. That works too. Now, how about drawing one more line through that point? That works. In a sense, these two are extremes, right? This one when we have just 2 lines, and this one where we have everything in between of 2 lines of the same color. These are 2 extremes and you can do anything in between. So there are actually infinitely many different solutions, essentially different. Now, the next question, which I have no idea what the answer to this question is it possible to do the same thing, only that each color is used on more than one point? Here we have only one point of one color, right? Is it possible to do it with more than one point for each color? As I said, I don't have any idea, and I don't want you to spend much time right here thinking about it. But of course I want you to think about it at some point when you have nothing better to do. And it's not math. Yeah?
I'm thinking something along the lines of like, if you imagine a coordinate grid on every dot that has irrational values, put a certain color, and every dot that has rational values, you put another dot, and then the rest of it. And then,
What do you mean by the rest? It's either, as
well,
far as
it's
I know,
literally,
numbers are
yeah,
irrational or
this guy, I
irrational.
like it, because I'm
Imaginary.
splitting two numbers, the number system into two disjoint parts. And then, I'm getting there.
Okay, as I said, this is for you to investigate. We are not going to investigate to find all answers here, and it's nice not to be able to find all answers at once, because otherwise it's too boring. Okay, so at least we see that, you know, we have lots of freedom. Even if we have some very weird conditions, we can still do stuff, right? Now, next question looks like much simpler thing. First of all, forget about the entire plane. The entire plane is way too many points, right? How about just one single circle? One single circle. When I say circle, it's not the disk, it's just the circle, the curve. So we have one single circle, and at the moment, all points on this circle are red, right? All points are red, but what you really want, you want to actually take green color. And now you want to paint every point on this circle either green or leave it red. So it must be, now we use exactly two colors. When you are done, every point of this circle will be either red or green. Now, all you need to do is to avoid creating an isosceles triangle with the same color. So when I say isosceles triangle, if you choose 3 points on that circle that you now painted, and imagine that those 3 points are vertices of a triangle, you want to paint your points in such a way that no triangle created like that is isosceles and of the same color. All three vertices are of the same color. Is it possible to do it that way? Yeah.
With concentric circles and colors?
What? No, it's just one circle. One
So you
circle.
just colored in using concentric circles, like alternating?
So-
maybe
No, it's
that?
just the
It's
circle.
circumference.
It's not
It's just
doing the
circumference.
interior, it's just like the exterior, the locus of points right now.
It's very simple. See, it's only one condition. You should avoid creating isosceles triangles with the same color. So three vertices. Yes, isosceles.
Meaning any point in that color
So
would
let's
be.
say
You were trying to look at the space inside.
It's like
I
half
mean, that's really-
Creating an isosceles triangle means that you can find any point in
If you take three, if you take 3 points on your
This point is
circle,
right over here.
and your
This point is red.
She was saying
This point is red.
if
This
they
is that.
if they are vertices of an isosceles
We're still talking
triangle,
about just the points,
they
but you
must
could
be
like
of
connect the
2
points.
different colors.
That's what she doesn't want. If this is red, red, red. That can be red, red, green, and then
This is gonna, so let's say I circle just this part. I would not be able to, I would still be able to do it. Well, I'm just saying, I'm just constraining it to this part. And no matter how small you make this, you're gonna be able to put 3 points right next to each other, which should create an isosceles triangle.
So you have to have alternating points, but then you've got lots of isosceles triangles.
It's impossible.
Why not?
I would say,
Why not?
if you just look at one little sliver of the circle,
Yes,
no matter how small you make that part of the color, that part of the circle,
yeah.
you're going to be able to take 3 points next to each other.
What do you mean next to each other?
Well, 3 points that are very small distance away from each other,
Yeah.
equidistant,
Yeah,
with one in the midpoint, which then would create an isosceles triangle.
yes.
So, and that's the extreme case, because you have like a little bit of red and a whole bunch of green, so obviously you'd be able to make.
No, that's not obvious to me.
Uh,
You know, if you say that you really take one part and completely, you paint the entire arc one color.
Right.
Well, and then the rest another color. I agree, you are absolutely right. In that case, you cannot avoid having produced these isosceles triangles. But who told you that it should be exactly, you know, the entire arc? Maybe you can take them, you know, like you suggested, some very bizarre scheme where not a single arc is of the same color.
Right, but I agree with what you're saying.
But
It
the
makes-
only other option, if you're not going to paint, so let's assume that they were discrete points, right? If you're not going to paint 3 points next to each other, or 2 points next to each other the same color, the only other option is to paint one green dot like we did in the last example, and then another green dot, you know, but then you're leaving that arc in between the other color.
No.
Maybe
No, the
there's
thing
dots,
is that
maybe
you are again talking about entire arcs. I agree that if you really paint it so that you have an entire arc, you are doomed. If you painted the entire arc, you are doomed.
So if you don't.
But what if there is no arc? If you do it in such a way that there is no thing, you know, not a continuous piece that is the same color.
So there's, then you just have single points. that
So
are
like
all
Alex
different
was
colors.
saying, paint the rational one color
Yes,
and irrational
yes.
one color.
But then you still have like alternating points.
So
Right,
what?
but you don't have a continuous arc.
Yeah, you don't have a continuous arc, so how do you know that if you're not, and you know, this is one example, you take points with rational coordinates one color, with irrational coordinates another color. It's only one possibility. There might be some other possibilities.
But if you have rational components,
We couldn't do that method.
That one wouldn't work because the rationals would.
yeah.
Because you could take any rational, I mean, you could do the extreme of like these guys thing 0, 1, 1, 0.
The thing is that you're just playing this game against somebody who is not to be named. We cannot name that personage, but he is extremely powerful and can invent very, you know, designs that will beat whatever you tell him. He will just invent designs very weird and very, you know, very complicated designs. No arcs, no continuous arc in his designs, but can you somehow, no matter what is done, no matter how that your opponent painted your circle, can you still make sure that there must be an isosceles triangle the same color? Good, great, sure. Okay, so there are some ideas.
And they're still always kind of different uses of art. You just get what they're doing.
Yeah, these two race points are still.
Okay, now, this is a nice exercise. If we had more time, maybe this would be just, you know, I would simply let you play with that, but we won't have that much time. What is your favorite figure, geometric figure? And when I say your favorite geometric figure, I actually mean, what is the figure that you know which is the richest? That you know that can, you know, it can be used for so many different things. Triangle is dull. It cannot, it's not reach. What is the reach? Little. The reach is little.
Space.
No, 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 no. Pentagon. Of course, regular pentagon. Regular pentagon.
Of
Now,
course.
why is it so reach? Well, first of all, it has to do with Fibonacci numbers. It has to do with, well, to begin with, it has to do with golden ratio. But then also, what do you know about its diagonals? All its diagonals are because of the same length from symmetry, right? And if you look at any triangle here, any triangle formed by the diagonals and the sides, what sort of a triangle is that? Isosceles triangle. Every triangle there is an isosceles triangle, right? Does everybody agree with that? Yeah. All right. It's actually even easier to see simply by taking 5 equidistant points on the circle. Just 5 equidistant points. Take 5 points. If you take any 3 of these 5 points, they will form an isosceles triangle, right? Right. Because if you take 2 points that are like, if you take 3 points next to each other, these 2 arcs are the same by our construction, right? So this will be isosceles. Another possibility will be to take 2 points that are next to each other and one which is 1 point over, right? But then this arc is the same as that arc. So this is isosceles again, right? Now what? If you have 2 colors and 5 points, you have these 5 points that you're just looking at, and you have 2 colors to paint them. It is unavoidable that 3 of them will be of the same color, right? And they will form an isosceles triangle with same color. Now, that was kind of easy. How about next question? What if we have 3 colors? Is it possible to paint all points on the circle using 3 colors so that we avoid all isosceles triangles with the same colors? Well, that picture will not work anymore if you have 3 colors. How about 5 colors? How about 25 colors? How about 1,000 colors? Now, it turns out that no matter how many colors we have, we will not be able to avoid producing isosceles triangles. Even if we have a billion colors, we will still produce inevitably isosceles triangles of the same color. Now, this is not as easy as this one, and the picture will not work. This picture will not work, and I don't know of any picture that will work. What will work is, and I don't know how to pronounce it, so Paul, help me. Theorem of, I know how to pronounce it in Russian, but it won't help. How do we pronounce it in English? Van der Waerden?
Yeah, I think Van der Waerden, but I don't know. It's Dutch, so.
Van der Waerden.
How do you say it in Russian?
Van der Waerden.
That's probably closer to the Dutch.
I think it's Van der Waerden.
Yeah.
Okay.
Yeah. But Americans always say Van der Waerden, but that doesn't mean that's correct. Yeah.
Okay. So there is this theorem that says the following thing: if you have a number line and you use any number of colors to paint every integer point, only integer points. We're not painting all points. We are painting only integer points. So you use any number of colors and you paint integer points on a number line with those colors. If you have long enough a sequence of those points, there will necessarily be an arithmetic progression of the same color. And in fact, it is possible to even calculate, if you are given m colors, what length you need to take so that there will be k members of arithmetic progression of the same color on that length. Is that clear what I said? Well, that solves the problem. Can you see it? That this solves the problem? Okay. Can you explain how that solves the problem?
I feel like this is what I was saying earlier. Like if you
Almost.
zone in on one little arc of the circle, blow that up, you essentially have a line segment. And then on that line segment, no matter how you arrange the colors, there's going to be 3 points that are equidistant from each other, like 3 points with 1 point in the midpoint. Right?
Now, how do you know that this is possible?
Isn't that the same thing?
Yes, it is sort of, but it is sort of the same thing. But you have to use that theorem. You have to say that, well, there is this theorem that guarantees that.
Okay.
And to prove that theorem is actually pretty difficult. It is a theorem that was proved in I believe it was in the 20s or 30s of the 20th century, and it was a pretty, the proof is not simple. The proof is pretty complicated. But that is a very powerful theorem, which is useful in many cases, in particular in that problem. Okay, so, but this was just, these two problems that we struggled with for a little while were not what I want to do. Those were just warm-up problems. The actual problem that I really am interested in discussing with you is the following. Okay. Suppose that we have a straight line, just one line. We don't have a plane. We have just one single line. How many colors we need? What is the minimum number of colors that we should use to paint each and every point on that line in such a way that any 2 points that are a unit distance apart are of different colors? Is my question clear? So you take a straight line and you paint every point of that line, and what you want to avoid having two points, exactly 1 unit apart of the same color. Just imagine that if that happens, there is some violent reaction and everything blows up. If you ever have 2 points of the same color, exactly 1 unit apart. We want to avoid that situation. We don't want to destroy the world, right? So, how many colors do we need? Is 1 color enough? Definitely not. How about 2 colors? Will 2 colors suffice to do that? To paint every point on the line and avoid having 2 points 1 unit apart of the same color? Just for, so that you have a scale, let me show the scale here. So the unit length is the length between any 2 of these marks.
Yes.
Will it suffice? How would you propose to do that?
Basically, if you just go on the integers
Yeah.
and do like black, white, open
Okay,
circle,
let me use red and green.
Okay.
Red and green. So what you suggest is, well, if this must be one of the colors, right? Let it be red. Then we know for sure that this must be green. All right. And then this for sure must be red, and this must be green, and likewise this must be green, this must be green, and then the green must be red. Aye, so far so good. But what about the rest of it?
And then you take each color and slide it to the right until the next one.
So what you suggest is all the points up to, but not including this one, must be red. Right? So all points on the interval from 0 to 1, well, 0 is included, but 1 is not. So all points on this half-open interval are red, right? And then you do the same thing with this one. All points on this half-open interval must be green. So all points from 1, including 1, up to 2, but not including 2, are green, and so forth. Right? Okay. Now, every 2 points that are exactly 1 unit apart are necessarily different points. Everybody agrees? So that was easy, wasn't it? Of course, there are other questions. Question is, here we are using these half-open intervals. Is it possible to achieve the same thing without using half-open intervals, using something else? So that is a thing that you might think about. Are there essentially different solutions to this problem? But what we actually did, we found what is known as chromatic number of a one-dimensional space, Euclidean space. And it was usually denoted by Greek letter chi, and then we put in parentheses the dimension. So what we found out is that chi of 1, dimension 1, is 2. It's the minimum number of colors needed to achieve this result. That we think we have one-dimensional space. We paint every point of that space using one of 2 colors, and no 2 points of the same color are exactly 1 unit apart. So
What did you call the pi number?
this is chromatic number of a line, or Euclidean space of dimension 1. It's the minimum number of colors that are needed to achieve that. You all told me that 1 is not enough, 2 works, so 2 is the minimum number that does the job. What will be the next natural question to us?
Right.
What about plane, 2-dimensional space? So the question is, what is pi of 2? In other words, it's just for shortcut, but the question is, what is the minimum number of colors needed to paint all points on the plane so that no 2 points 1 unit apart are of the same color? Will 1 color suffice? Will 2 colors suffice? 2 colors? Why not? So somebody said that pi of 2 is bigger than 2. Somebody said that, I heard. Which means that if you have only 2 colors, it is not enough. Why not?
Turn those line segments into stripes.
Well, you wouldn't have to.
Yeah.
I know, but if you can find a counterexample.
Yes. What is your counterexample? You know, the counterexample. Wait a second.
No, you have to show it does not.
You have to
There's
prove
just no
that
color.
no matter how somebody colors it, it will not work.
So,
If your coloring doesn't work, it's no good.
because we're talking about the minimum number.
Minimum number of colors. Minimum number of colors
Okay.
which you need to use to avoid producing 2 points at exactly distance 1 apart of the same color.
I have a proof.
Go ahead.
You have a point that's red.
Okay.
By necessity, if you're only using 2 colors, you would draw a circle of radius 1 around that point.
Okay.
And
It
there's
must
2
be green.
points. There are
Yes.
2 green points that are 1 unit away from each other in that diagram.
Yes. It's clear, right? That if you take 1 point here and you just swing same circle, say around, you'll have another point which is green and which is at distance 1. Another way to think of that, and this is the same thing, of course. How about just equilateral triangle? Take take an equilateral triangle of side 1. It's the same thing. Take equilateral triangle of side 1. It has 3 vertices. 2 of them must be of the same color. We have only 2 colors, right? So that's proven, right? We know that this is true. This is certainly so. How about 3? Can it be 3? Is 3 different colors sufficient? Okay, now I've given you the handouts, right? Everybody has a handout? There is a picture. There is a picture at the bottom. Look at the picture at the bottom. The picture at the bottom of the first page. What does that picture have to do with the question? What does it have to do with the question? doing with that picture? People are doing something. What are you doing?
Labeling,
Labeling?
Yeah.
By what?
3 letters.
By colors. Labeling the vertices, these points? The points? Or what? Okay, yeah. Yeah. So can you paint just these 7 points using 3 different colors so that no 2 points at distance 1 are of the same color? Can you do that?
Yes.
You can?
Yes.
You can do that using 3 colors?
Yes.
Can you instruct me how you do that? Now, by the way, the way this picture is constructed is we start with an equilateral triangle. So you start with one equilateral triangle of side 1. You put another one on the other side, and you produce 2 of these rhombuses. And then you place these 2 rhombuses at the same point, and you move these 2 points out so until they are at distance 1 also. Is that clear? So this is an equilateral triangle of side 1. This is another equilateral triangle of side 1. This is 1 more. This is 1 more, and this distance is 1 as well. So can you paint these 7 points using 3 colors?
No.
Lisa said no. Lisa, can you explain why?
No, because I think there are places where you've got 4 points of intersection.
Now how would
I'll
you
explain
suggest?
it. You can start with the top point,
Yeah,
assign it like B for blue,
okay.
and then the argument is that those bottom 2 points have no choice but to be, no, the bottom 2.
Oh,
They
But-
now have to be both blue.
yes, because suppose that we have colors B, A, what color is A? Good. A and C, cherry, okay. So we have B, A, and C, these are our colors, right? Okay, these 2 must be
AC.
A and C, we don't care which one, right? This can be C or A, and this must be the opposite. This must be then A or C, correct? Everybody agrees with that?
Yeah.
Which forces this to be blue. This must be blue then. But likewise, this must be blue, if you consider this. And therefore, these 2 must be of the same color when done. It is impossible to paint even these 7 points. And if it is impossible to paint these 7 points, it is impossible to paint the entire plane, satisfying our condition, right? So what does it tell us? 3 colors is not enough. So now we know that pile of 2 must be greater than 3. We need at least 4 colors. So in fact, I don't really like writing greater than 3. How about simply is greater than or equal to 4? And it's the same thing, right? We know that we need at least 4 colors. Well, we're doing great progress, correct? A little bit more and a little longer, and we'll figure out what that is. Now, I really like you to look at your second page. Just turn it over, and you have some few pictures there. On the opposite side of the page, you have some designs. And I'm going to use the simpler design, just that 3x3 square. And what I'm going to do is the following. I claim that this picture, this 3x3 square, can be used to see that 9 colors is definitely enough. If you give me 9 colors, there is no problem to achieve what we want. In other words, that picture will really explain why this is true. Now, can you tell me why? Why 9 colors will be sufficient if we use that, if you look at that picture?
I guess if you can imagine infinitely small points like that, and then you take that little set of grid, you could tile the entire plane with that. And if each of those squares is a separate color,
Okay, okay. So I like some of the ideas that you described, and I think that maybe I like all of them, but I simply didn't catch all of what you said. So let me just tell me whether this is what you meant. Suppose that we have infinite supply of tiles of this design. So this is my sort of modern tile. I have infinitely many of those, so that I can really paint I pave the entire plane with these. And then suppose that each of these tiles is painted using 9 different colors. This little square is color 1, this 2, this 3, this 4, 5, 6, 7, 8, 9. Yeah?
What's the side length of the square?
That's a different story. That's a different story. But suppose that we have that, right? Now, there is another question that we probably should have asked before even asking that question. What about the lines? What colors are the lines? Because we need to paint, remember, we need to paint every point. So the question is, what are these points? Well, it really doesn't matter. It really does not matter. We just randomly assume that, let's say, these are definitely color 1. These two can be whatever, either 4 or 2, doesn't matter. And same thing for all of the lines in between. But now we definitely know what is what, right? And then Mark asked, what is the side? What is it we really want?
The diagonal to be less than
We want the diagonal to be less than 1, right? Is that clear that we want the diagonal to be less than 1? Everybody agrees with that? Because if it is bigger than 1, or equal to 1, then we have two points of the same color, right? But if this length is smaller than 1, then all points within that one single little square are distance less than 1 apart, right? Okay, let me just do something like, suppose that the side of the square is x. We want the diagonal to be bigger, be smaller than 1. What's the diagonal of the square of side x? Yeah, so we want square root of 2 times x to be less than 1, right? What else do we want? Now this is one single tile, but we want to use all of these tiles to tile the entire plane. So when we place the next one right here, right? So what is it? And this is color 1, 2, 3, 4, 5, 6, 7, 8, 9.
So we want x to be greater than 1/2.
We want these 2 points. You know, this point is of color 1. Of color 1, and this point is of color 1, right? So we want this distance to be bigger than 1. So we want 2x to be bigger than 1. But any x that satisfies both of these 2 inequalities will work. Can we find an x that does both of these 2 things? So this gives us x is less than 1 over root 2, which is approximately 0.7, something like that. And this gives us that x is bigger than 1/2. And of course, there are numbers that satisfy both. And any of those numbers will work. So, that proves what we want. Wait a minute. Maybe this proves, how about, why should we use 3 by 3? How about 2 by 2? Then only 4 colors will suffice. Can we do that? Can we do that? Why not? So, question. How about just using this model file, where we have 1, 2, 3, and 4? What's wrong with this? You know, if this works, then we're done. Then then it's greater than or equal to 4, less than or equal to 4, equals 4, right? So what's wrong with that? Or maybe everything is fine with that.
Well, you still have the bottom range, x is less than 1 over root 2, but you don't have it.
So in
You don't
here,
have the space.
we want, if this is x, we still want square root of 2x to be less than 1. But if we place another tile next to it, then we'll have, this is 1, right? So what is it we want?
X is less than
We
greater
want
than
that x to be greater than 1. Or even simpler than that, we simply want the diagonal of the square to be less than the side of the square. Doesn't happen that way. Okay, so this doesn't. All right. So, well, still, we are, in a sense, doing very well, because we know that it must be one of these 5 numbers: 4, 5, 6, 7, 8, or 9. In fact,
Don't we now change the 4 to a 5?
what?
I thought we just proved that you can't have 4.
No, this design doesn't work.
Oh, right, we can always
Just
find
that
a
design
single-
doesn't
I'm
work.
thinking counterexample versus.
Okay, now, how about these 2 little designs? What these 2 little designs have to do with anything? And of course, these are supposed to be regular hexagons. Sorry about distortion. It's not me, it's the computer. These are supposed to be regular hexagons. And what does it have to do with the question we are struggling with? Any volunteers to come over and explain what the pictures have to do with the question and what they tell us and how, what's happening? Any volunteers? I completely saturated with chalk, so hard as I may try to put more chalk on myself, it won't work. So somebody else might step in and we'll say, okay.
So this has to be some color. And then this has to be a different color. And basically just like the tile. These all need to be different. Am I just jumping too much?
No,
Right,
it's
prove
everything,
that.
you explain everything. So, you mean that this is your mother tile, right?
Right.
So, do you see that this is mother tile, which is of this complicated structure? Now,
Oh wait.
But 6 could be 3 and 7 could be 4 and 5 could be 2.
what?
No, you can't wait. 6 could be 3, 7 could be 4.
But when it's all by itself, 4 colors.
Oh, you are using just 5?
5 could be 2. And it's just in that when it's all by itself. I'm not saying the bigger picture.
Actually, I mean, depending on how long you make the side length, because what we're going to end up doing is making this length just under 1. And if this length is just under 1, then this length is going to be
Okay.
shorter.
Okay, now I have to, actually, I need to,
You can't do this.
because I don't quite follow you.
Mm-hmm.
So, thank you so much.
All right.
Danny, thanks a lot. You probably should stand here and help me. I'm trying to interpret what you're doing. So, what is going on, I believe, is that we do start with this one single mother tile, which is of this shape. And here is our mother tile, and let me just indicate that this is one single mother tile. Right? Now, first of all, can we actually pave the entire plane with this tile? Will it fit?
Yes.
Everybody believes that if we have a tile, just infinite supply of tiles of this shape, each one consists of 7 regular hexagons, then we can pave the entire plane with those. Everybody agrees with that, right? Okay, fine. I believe you at the moment. I'm not sure that I'm completely convinced, but just imagine that you're right. And then Daniel suggests to paint this mother tile with just 5 colors,
No,
right?
no. This I was thinking
It's 7. It's 7. Why 5 was not enough?
Actually, so that's a better result. If you want to extend this to the rest of the tiles being put in,
Yeah. Yes.
just do the borders of those. So if you make that a 4, then you're getting a 4 next to 4 when you're putting the next tile.
Can't she use a 4-color map there?
What?
Can't she use a 4-color map there?
I'm not sure. No, you can't. You absolutely can't. Because the thing is that the design can be anything. They don't have to be connected. They don't have to be continuous areas. Okay.
So this is definitely going to be a 6 and a 7. And then we're going to repeat that pattern. So then,
Yeah.
so
Yeah. So for example, right? Yeah.
But why do you need to repeat the pattern?
Because this is the same tile. This is the
I
same
know
tile.
that, but can't we just go from this to an explanation?
He wants to show the bounds for how far apart and how close together.
Okay.
Yes, exactly.
now I'm just losing it.
Actually, it's much easier. It's much easier if you do something like it really doesn't matter, but how you do that. But it will be easier to argue if you simply did it this way. So this is 1, 2, 3, 4, 5, and then if you do the same thing here, it's 4, 3. I don't like that. I will, just for simplicity, you don't need to do that, but it will be easier to see what's happening. So if this is 1, so we already decided that this is going to be 1, 2, right? Okay, now how about doing something like 3 here, 3, 4, 5, 6, and just shift it. So this will be 2, 1, and then what's left? We already have 3, 4, 1, 2, and 6, 7 is that okay? No, I think 7 would be better here. 7 would be here, and then what's left?
5, 6, and
5 and 6, so we'll have 5 and 6. So doing that is then easy. It's really easy to see how it paves the whole thing. Can you see that? But again, since our numbers are just symbols, it really does not matter. We don't really have to do them in this order. Everybody sees that? How this, now we can see easily that this paves. So, this must, wait. Yeah, this must, but then this is probably not
Yeah,
our.
that's ordered.
Okay, now let's see. So this is our motherboard, right? Here we
Oh, there should be
have
a 4.
our motherboard. Those were no.
Yeah,
wrong.
sorry about that.
Those were wrong. Why? How can we see that those are wrong? Well, the colors, if we just continue that, we'll have here, we must have 3, 4, 5, 6. On top we have 6, 7. And here we have 7. And then what? After 7, what goes after 7? 1, 2, and so forth. Okay, can you see where? And at the bottom, how can we continue at the bottom?
4.
How do you know that it's 4?
4.
How do you know that this
It's on
is
the
4?
side.
I don't.
Up on the right. You have 6 and 4.
Yes, it just we have 6 and 4 going that way, so we must have 6 and 4 going that way.
That reaches.
And then we have to have 5, and this is
That's not right.
wrong. This is wrong because this must be 4, and this must be 3, and this must be 6, and this must be 5. Okay, now can we see any other mother tiles here? Where is another mother tile? 1 is in the middle, right? 1 is in the middle of our mother tile, so this is the middle. Then we have this, that, this, that, this, and then this. This is another mother tile, not this. Is that clear?
Still confused.
Okay. I am drawing this red boundaries. I'm drawing red boundaries between the mother tiles.
Tell you what confuses me though.
Yeah.
Are you trying to just make it so that each hexagon is next to another hexagon of a different color?
No. What I'm trying to do, I'm trying to use my mother tile, and I'm trying to show that how this mother tile fits with the next one. My mother tile consists of 7 hexagons, regular hexagons. This is by tile.
I understand that.
Yes.
But isn't the ultimate goal to get adjoining hexagons different colors?
Oh yes, sure. Not only that.
So like the one tile needs to be 1 unit away from the other one tile.
We want this same tile without changing the coloring scheme to tile the entire plate. So on this tile, the coloring scheme is as follows. We have 1 in the middle. To the left and on top, we have 3. To the right on top, we have 4. So here we have another example, another copy of the same tile. 1 in the middle, 3 to the left, 4 to the right.
Okay, let me tell you what
Yeah.
confuses me.
Yeah.
Don't you want it so that it's always less than 1 from any point inside one hexagon, any other point inside the same hexagon?
That will be now our next goal. First,
Okay.
the first goal is to simply show that if we have this tile, if we have the tile that is painted these we can use the same tiles without rotating them, and paint the entire plane using the same design. Same design.
Okay.
That's the goal. Like we did with the square. That was easy because with the square we simply shifted it vertically and horizontally. Here we actually shifted. See how we shifted? We shifted slightly down in one direction, and then the next one will be shifted up.
And my problem is, why is that necessary? Why can't you just use a four-color map there? And
No,
just-
we can't.
You didn't explain, can you explain why though?
I told you. I told you because now in the four-color map. What do you mean by four-color map?
If you have a map in color with four colors,
Yes.
so that no adjoining countries have the same color.
Yes.
Okay,
Yes.
so isn't that good enough?
No.
Okay,
We
so
want we want any 2 points distance one apart to be of different color. That's what we want.
The four-color theorem talks about boundaries, it doesn't talk about coloration of distances, so.
We want every 2 points, every 2 points, exactly 1 unit apart to be of different colors. That's what we want.
Well, why can't you have it so that inside one hexagon,
Yes,
okay, you're less than 1 unit apart, any 2
Yes.
points inside one hexagon.
yes,
But if you go more than 1 hexagon
yes,
away,
yes.
you're gonna be more than 1 unit apart. So in other words, like if you're going from a point,
Okay, so what is it you're suggesting?
if you have a hexagon,
Yes, you have a hexagon.
okay,
All right,
and if you go 1 unit apart from any point, you'll be in
Yes.
an adjoining hexagon.
okay.
Pick any point,
So, are you telling us that that 4 colors is enough?
I'll try, or can you explain why not?
Okay.
Can you set it up so that any
Okay, so
point,
this is color 1.
pick any point in a hexagon, pick a hexagon, pick any point in a hexagon.
Okay, now what? Let's just start with your hexagons. You said you have just, you pave everything with hexagons, right? Now,
Okay.
we forget about the mother tile, there is no mother tile, there are just hexagonal tiles, right?
Right.
Everybody is with us? Okay, now, so we just have these hexagons. Alright. Now, how would you propose to paint your hexagons? So you imagine that the entire plane is paved with these hexagons.
Okay,
So, and you propose to paint this first color, right?
right.
Now, this one will be,
Well, we know that we can paint it with 4 colors.
okay, you want this second color. Is that what you want?
Yeah.
Okay. How about this? Which color do you want that?
Okay, well,
It's up to you.
Make
Just
it
tell
one.
us.
yeah, what I'm asking you is to say why the 4-color map there won't work. Because I'm assuming,
Because it doesn't talk about what we want.
because I'm assuming
Yes.
that you can make the hexagon small enough so any 2
Yeah.
points inside
Yeah,
it are
yeah.
less than 1 unit apart.
Yes, yes.
Now, this may be bogus, but is it possible that if you go from one hexagon to another, it's adjoining, there will be a point there. If you go to 2 adjoining hexagons, there will be
Yes.
2 points that are 1 unit apart.
Not if the hexagon's less than.
So what I'm saying is, can you be within one hexagon and be less than 1 unit apart?
Yes,
But any point in a hexagon
yes.
will be 1 unit apart from a point in an adjoining hexagon.
Yeah.
So that's what I wanted, I kind of want that ruled out.
So you're talking about sort of like how we colored the line, as if you had like the boundary would be included,
Yeah.
but then you would have to not include the boundary in the next one, and then those 2 boundaries would be less than, would be like 1 unit apart or less. So
I have
we
a,
can-
I have kind of a different explanation.
Yeah.
If you look at on the first page, the master spindle, Mosher's spindle, what you're kind of doing is you're taking that red dot, the dot at the top, and you're rotating it around that dot in some respects, right? So you're taking that equilateral triangle thing and then kind of spinning it so that there's another one until these are the same distance away. Now, what I started working on was like, if you do that with a red dot in the middle, and then a green dot and a blue dot, and you take that shape and you spin it until it's just under 1 unit away. Now you have like a green and a blue and a green and a blue, kind of like a pinwheel shape. But that doesn't work because you have have in the corner of the pinwheel, there's going to be like a green and a blue, like this green and this green are going to be exactly 1 unit apart and then move into the circle. Right, so they need to be different colors to go around. And then the bigger issue comes when you go out a little bit. Like basically all of these shapes, these two are tessellations, which is why we're doing squares and hexagons, because you need to be able to tile them onto a two-dimensional surface without overlap. And so you have these circles that are kind of like, I mean, I just drew the one circle, but then you can have like, from this red another circle here, and then from this point another circle here, and all of these one distances away from each other. And the problem comes out here when you're farther away from the center of the original tessellation, where now these are obviously going to be more than, like, if I just swing it, right, the distance becomes more bigger as I go further away from the center. So then, you know, if you do the 4 colors, basically, I mean, what you're basically saying is that if you only have 4, there's no way to arrange them into one shape, because you know you need to use tessellation. There's no way to put into one shape such that when you put the same shape next to it, you're not going to have that one distance problem in the next shape over, even though they won't be touching each other within the same shape. Does that make sense?
I don't think we can bother with that. You really slow it down. Actually, you know what I mean?
Yeah.
It's just like
All right, can we, is everybody convinced that at least with this model file we can do what we want, or no? And how are you convinced? Why are you convinced? So first of all, I think that it is kind of clear that we can really play the whole thing. Now, what sizes do we want? What is it we want to avoid? Like in the previous case, what is it we want? We want that the diagonal be less than 1, right? And so the diagonal in this case is exactly twice the side, right? That's clear. Is that clear to everybody? So the side is x and the diagonal is exactly 2x, because it's made of a collateral triangle. So we want 2x to be less than 1. And now let's see what are the closest points of the same color. Which two are the closest ones of the same color in your opinion? So if you look at let's say this color and this color, these are the closest regions, right, of the same color. What are the closest points of the same color? I'd say definitely it's one must be some corner, right? So let's say this corner, right? And which?
No, the one.
Oh, this corner here, right? This corner is closer. And then another one is this one, right? Okay. So what's the distance between these two? What is the distance between these two? You should find it. Find it. You need to use a little bit of geometry. These are regular hexagons, of course. And from symmetry, this will be the midpoint, right? And you find this distance. You need to find this distance. You know this angle, right? You know this angle. This is 120, right? This is 120. These are congruent triangles. And you know that this length is x. This length is half x. Because that was midpoint. And this is 120 degrees. So please do find what is the length of this. The way it's written, of course, you can use for cosines, but you can probably find something easier than that.
just tried asking Wolfram Alpha for the chromatic number of the plane.
Oh, don't.
It's wrong. It gave a wrong answer.
Oh, really?
Yeah,
Great.
that's what it's. Well, it didn't really understand it, but it still gave a number.
Oh, okay, great.
And what number did you?
That's wonderful. Not understanding, but
Yeah.
giving an answer.
Yeah, I know. It gave the number 4.
Okay, anybody?
Well, maybe it was more than we knew.
Root of
Yeah,
root
maybe.
7 of x? Yes. Everybody agrees? So what we want is root 7 of x be greater than 1.
Any questions?
And so we know that
Terrible.
x is less than 1/2, but bigger than 1 over root 7. And this is possible. This is possible. So, what does it prove? It proves that 7 will suffice, right? Okay. And this is all what's known. It is all what's known up to this point. Nobody knows better than that. It is known that pi of 2 is between 4 and 7. It might be 4, 5, 6, or 7. 4, 5, 6, or 7. And nobody knows what it is. In fact, some people started even thinking that we have here something that really shows us that our axioms of Euclidean plane are sort of deficient. That depending on how we define finer our Euclidean plane, it can be any one of those 4. With defining, we can simply postulate that it's 4 and it will be one geometry. We can postulate that it is 5 and it will be slightly different geometry. We can say that it's 6 and it will be another geometry. And we can say 7 and it will be one more geometry. Euclidean geometry.
You still follow all the other Euclidean axioms.
Yes. So nobody, people have been trying to see what it is using all sorts of powerful mathematics. And because they explored so much trying to figure out, it led them to believe that it might be that. It might be that our Euclidean geometry can be really split.
That's just a
into these
conjecture
different-
right now.
Yes, it's a conjecture, and some people don't believe so, but some people started thinking that. Okay, so in the past I was making this mistake of giving all 3 pages right away to people, but now I'm not doing it anymore. So here's some concluding remarks. And what this belongs to, these kinds of problems, they belong to what is known as geometric combinatorics or combinatorial geometry, and there are lots of open questions there. A lot, and just and they are very easy to state. All these questions, they are widely open. You can try to investigate it on your own or with your students, and there is always room to investigate. And I mentioned several more problems that are easy to state and still are that are still open.